Okay, so this week I have 6 problems. The first and the last one are a little bit different, but the 4 in the middle, they are all kind of related, and there's a bit of a theme here. So let's look at the first one. It's meant to be a warm-up, but maybe it's not absolutely the most obvious what to do. So let's see. So Gunnar and Emma, we're going to play this game. They each have one die. Sorry, two dice, and each dice has numbers between A and B, and each of those numbers may occur equally likely. And so, if each person rolled a 2 die and add up the numbers, who is going to win more often? That's basically the question, right? So again, I assume that you've read the problem, and there are multiple ways you can tackle this. The first way is to simply generate all possible rows, because it says here that each of these rows, A and B, are at most 100 and at least one. So that means that in the worst possible case, each die can have at most 100 different combinations. So if you, not combination, but 100 different possibilities. So what you could do is just generate all possible um, sets of values for the 4 dice row, figure out who is winning, figure out which one wins for each one, and then count how many times Gunnar wins, how many times Emma wins, and then basically do that. If you do that, right, so there's a 1 second, there's 100, but 4 dice was 10 to the 10 squared raised to the power 4. So the worst case is 10 to the 8, which is 100 million, but 100 million for very simple things. It might be good enough. I'm actually not sure if you simply write sort of 4 nested for loops that goes through the possible values of the 4 die. Now you can do things a little bit um, smarter if you want. For example, you can generate all possible um, rows that Gunnar can have, and then all possible rows of the first die of Emma, and from that you can figure out how many of these, using some arithmetic to figure out how many of these rows could make Emma wins or Gunnar wins, and so on, and that will reduce your time to be n cubed, where n is the number of possibilities for each die. So that would reduce it to 10 to the 6, which is definitely plenty. Now, there is actually a better way of doing this. So, because everything is equally likely, it turns out that all you have to do, and maybe you can think about how you prove that mathematically, to figure out the expected value for the scores of each person, which is the sum of the expected values of each die. And then all you have to do is compare. If one person has a higher expected value than the other, then it's more likely that person will win. And this works because every possible row, it's equally likely. So with that, how do we approach this, right? So we can actually deal with the row of the 2 dice separately. If you have a die that can go anywhere between A and B, then I guess the expected value, because everything is equally likely, is just the average, which if you can work it out, or if you look at this, it should come out to just A plus B over 2. So the expected value for a single die row is just A plus B over 2. And if you have 2, right, you have 2 dies, A1, B1, A2, B2, right, you just do the same thing. And then you add them together, and that's the expected value of the score after you roll 2 die. So you would compute 1 for Gunnar, one for Emma. So that, I know that I'm writing A1 and A2 and B1 and B2 twice for each one, but uh, the numbers for Gunnar and number for Emma are obviously different. And the question is, which one is bigger? Now, whenever you divide, okay, whenever you divide, you have to be concerned that if, if you have an odd number, if you just use normal integer division, you will lose a half somehow. But because we're just asking if these two things, which one is bigger, you can actually completely avoid this issue by multiplying both sides by 2. So the denominators go away. And you're just comparing A1 plus B1 and A2 plus B2 and which one is bigger. And that is all you have to do at the end. Okay, so there's a little bit of thinking involved, but in terms of coding, it should be fairly straightforward. Do not do division by 2. You can get away with using division by 2 if you use doubles, floating point numbers, because dividing by 2 is safe and there's never a rounding error because numbers are represented in base 2. But if you want to stick to integers, you can just multiply everything by 2 and you never have to worry about dividing. Okay, so that's that one. As I said, this is sort of a little bit of a warm-up problem. But let's look at the other ones. Okay, so here's the problem is about a keyboard that somebody, when they start typing, they typed everything one position to the right. So Q is like this W, J is typed K, and so on. And you're given a message in this in this mistyped fashion, and then it says that the input consists of several lines of text. Each line may contain digits, spaces, uppercase letters, and punctuation, except backquotes, tab, backspace, and control. Now, why are these particularly problematic if they exist? Because here, if you look at the keyboard, if you see Q, A, and Z, Q, A, and Z, and then the back quotes, right? You're supposed to have mistype everything by going one row to the left, to the right. So to correct that, whatever they give you, you should step to the left. But back quotes Q, A, and Z doesn't have a corresponding character to the left. So if you see them, that means that you have you have no way to correct it. So that's why you cannot have those as input, which is good. So basically, if you see a 5, you know that you're supposed to go to a 4. If you see T, you're supposed to go to an R. But if you see space and punctuate, if you see punctuation like the single code, you're supposed to do semicolon, etc., etc. The only thing that you're not supposed to change, of course, is space. So this is not a problem that is algorithmically challenging as such. Right? Most people after 1620 should be able to get this done one way or another. But what I wanted to show you, I guess, is that there are many different ways you can do this, and I want to show you the better way. So if you're just starting out, it might be tempting to write a bunch of if statements. If you see a 2, print a 1. If you see a 3, print a 2, and so on. Or maybe you move a little bit further and you say, well, these are just a bunch of cases, so maybe I use a switch statement. But in any case, you have to write basically one case for every single possible character, and not only is it a pain, it could also be error prone, and you might mistype something. So what is actually a better way? A better way is actually just to code the layout of the keyboard somehow, and then we will simply search. If somebody gives you an R, you just search into this table of the layout of the keyboard, find out where R is, and then just look at the one to the left. And you might say, well, this is actually a little bit slower because you have to do a search, and that it's true. It's slower than just using a bunch of if then else statement. Well, actually, if then else, it's also a search in disguise because you have a lot of if then else. But if you use a switch statement, there's no search. So you might say, well, switch statements are more efficient, but um, because you only have a very small number of uh, characters in the keyboard, it is actually good enough. If you really, really have to worry about this, you could do it anyway, do what I'm about to say anyway, and then before you start actually doing the translation, build a more optimized table that allows you to just look things up directly without searching every time. So anyway, how am I going to do this? What I'm going to do is I'm going to encode this keyboard as a string, all the keys, all the letters that I care about. Now you can, if you want, encode it as 4 strings, one for each row. But in this case, it's actually not necessary because all you have to do is encode this into one single string, look up the character, and just report the previous one. Where can it go wrong? It can go wrong if the input character is the start of a row, and then when you look at the previous one, it will be the last one from the previous row. But we know that this is not possible in the input, so we're safe. So let me show you how I end up doing this. So as you can see, I simply coded the keyboard as a string. Now you might say, why is it one single string? So in C++, when you write strings like this, right? So I have write strings like this, and I just put them side by side with no additional operators, then automatically concatenates them, right? So I basically just go through my keyboard. Of course, you have to be careful that your keyboard matches the keyboard that's actually printed, and just type one character at a time, right? The only thing that you have to be a little bit concerned about, it's here, because a backspace means something special. Sorry, a backslash means something special in strings. For example, if you say backslash n, backslash something else, backslash n means new line, backslash something else. There are many different things you can do with backslashes. These are called escape sequences. So if you just put a single backslash, that's not what you want. It's trying to escape something. But 2 backslashes in a row, that's the actual backslash character. Okay, so basically I have one single string that represents a keyboard, and then I have this lookup. So you give me a character, I tell you what comes before it. So I'm using a string search function to look for that character. And if it is not found, so string search in C++, when you try to find position, it will return this special constant string : n post to mean that it's not found. So if it's not found, like a space, for example, I'm just going to return it unchanged. Otherwise, I'm going to return whatever is in the previous position of the string, which effectively gives me the character one position to the left. And then the main routine, all I do is okay, so it's important that you use the get function to read characters, because if you just use the arrow extraction operator, you will skip through all the spaces and new lines and so on, whereas this will not. So basically, I just keep reading characters and then translating it. Notice that new line characters, if there are multiple lines of input, right, so several lines of text, there will be new line characters at the end of each line in the input, which when I come to here to look up, it will not find it because I don't have new line anywhere here, and so it would just return the new line as is. So again, this is not necessarily a hard problem, but I want to show you the technique to make things a little bit easier to write and easier to get right. It's much easier to get this thing right than to verify across I don't know, 40 cases, probably stretching multiple screens, that everything is taken care of, everything's correct, and you're not missing a case, right? Okay, so that's this one. Now T9 spelling, again, I assume that you have read it, the problem. It follows the same kind of idea. I have a string, hi or yes or foobar or whatever, and I need to convert it to a special way of typing this. So for example, H, if you look at this keypad, H is the second letter on the for the digit 4, so you press 4 twice. That's how you can get H. If you want Y, you need to press 9 3 times, right? So again, you don't want to write 26 cases, one for each letter, and hard code that in. But if you actually just somehow store this keypad data into some kind of a table, we can make our code a little bit easier. Okay, so what else? So sometimes you need a space to separate it, right? Because if you just have 2 4s followed by 3 4s, but you don't have space, then you can't really tell when you just have a sequence of 5 4s how it breaks up. So whenever you have the same, okay, and then also 0 emits a space, and then also, insert two characters in sequence from the same key, user must pause before pressing the key a second time. So you need to insert a space. So we have to translate all of that, and then also remember what is the last thing that was pressed, so that if you are pressing that again, you have to insert a space. That's basically it, right? So how do I represent this table of? There are many different ways I can do it, but the easiest for me, the easiest way is just have an array of 10 strings, one corresponding to each key, each digit. Right? So for 0, it means space. So there's a space here. 1, it's not used, so there's nothing. 2 is A, B, C, D, E, F, and so on. Okay? So now that I have this data structure, I have to write code that figure out how to convert a single character to a string. So what do? You give me a character. I search through each of these strings. Again, I use the string search function to figure out if if the characters in that string or not. Otherwise, I move on to different number, different key. And if it is not found, so that this means if it's found, then I'm going to make a string that's based on 0 plus I. So 0 here is the character 0 plus the value I. So if I has a value 5, this is the ASCII character 5. And this will create a string of this character repeated that many times, right? So if it's found at position 0, that's the first character. So I need to create a string of one of those digits. If it's position 1, that means it's a second character. So I need to produce 2, etc. And then here, assert false. Assert, if you don't know what it does, it checks the Boolean condition inside. And if it's false, it will crash. And if it's true, it will keep going as if nothing has happened. So it's a good way to check if certain condition that you think should be true is true. And if not, your program will crash immediately and tell you this is a line that it fails. So why do I put assert false when so this is guaranteed to be false? Because I want to make sure that this loop never exits. It would always exit by finding one of the characters and returning it. And if this loop ever exits and reach here, it means that I gave it a character that cannot be found here. So maybe I have some incorrect logic, or maybe I wrote the table wrong. So this is what I guess we call defensive programming, just in case something goes wrong, we catch it. Okay, so in terms of solving it, okay, so here, just read in the number of cases. Then we got to ignore that trailing blank new line. I think we talked about that either last time or the time before. And then solve it for each case. Why do I need to do that? Because each case, it's a line of text that have spaces, so you need to use getLine. Okay, so here I read the message. I remember what is the last digit I printed. So at the beginning, the last digit I printed is nothing. Then for every character in the message, I convert it to the string, and then I check if the character that I am about to use, the digit I'm about to use, is the whatever I just printed before. And if so, I print a space, otherwise I don't. Then I print the translated string and then remember the last thing that I just printed so I can check when I need a space for the next one. So again, I don't think this is algorithmically challenging, but it is a little bit easier to code it in this way. You might say, well, what if I have a table instead of this? I have a table of 26 or even 27 characters, the 26 letters plus a space that convert to hardcode the string. Then I guess you can do that, but then you have to remember you have to do 27 things. Whereas here, it is relatively easy to see whether the table is right, and then with a little bit of extra computation, you will grab the correct translation. Okay, so I just want to kind of, for this problem and the one that we just did with the keyboard, basically I want to show you the technique of using table to simplify your code. When I say simplify the code, I don't mean make it run faster. I mean that the logic, it's now something that's applicable to every single case. So you write the code once here and let the table deal with things, as opposed to not having a table and you write basically different logic, different code for each of the 27 cases, in which it's a lot harder to get right and make sure that you didn't miss anything. Okay. Okay, now the next two, they're both something about chess. And in this case, basically you have a bunch of chess pieces, in this case queens, and you want to know if they attack each other. What does attacking each other mean? It means that two things attack each other if they're in the same row, okay, or the same column, or diagonally. Okay, so you can go same row, same column, or same diagonally. And because it says it is solution 8 queens problem, you also have to make sure there are exactly 8 queens. Right? So if they give you more than 8 queens or less than 8 queens, you tell them no right away. All right. So the question is, how do you know if there are two queens that attack each other, whether it's row, column, or diagonal? You could easily say, well, for each queen, just look at the 8 directions. Right? Just scan all the 8 directions and see if you find another queen. And that's possible. But there are more efficient ways of doing this. I want to show you a different idea. So here's your chessboard. And you have a queen here, maybe you have a queen there, and so on. Now, how can I easily figure out if I have two queens on the same row? Well, one way to do this is to say, have a row array that has true or false, or if you want, a count of how many queens you have. And what am I looking for, right? What am I looking for is is there any row that has more than one, right? If I see that any of these entries is bigger than one, I know that I have two queens on the same row. Therefore, I can say invalid. And notice that I can just scan this one from left to right and see where the queens are. As soon as I see a queen, I can go into the corresponding entry and increment it without ever searching left and right. Is there a queen there? Is there a queen there? I don't have to do that at all. So if I were to have to scan left and right to find a queen, that means that I would have to have basically an n cube time algorithm, assuming that you generalize this to n by n with n queens, because you're going to go scan every single position, and for each one you scan the whole row. So it'll be n square queens, n square places to scan, or to start the scan, and then a big O of n time to scan. But if you just do what I said, you can, in constant time, figure out the correct entry in each row and increment it, and then that drops it down to n squared. Okay, but there's nothing special about checking for rows. You can have another array to check for columns, right? How many things are in each column? And again, right, 0, 1, 1, 0, 0, 2. And as soon as you see a number that's bigger than 1, you know that you have more than one queen in this column. Now the question now is, what about diagonals, right? Because rows and columns are pretty easy. Just look up an index and that's it. Well, there are two kinds of diagonals. There are these type of diagonals and that kind of diagonals. If you look at this type of diagonals, you look at the row number and column number, you will see that here, along this diagonal, the row and column numbers are exactly the same. 0, 0, 1, 1, 2, 2, 3, 3, and so on. What about this diagonal? In this diagonal, R is always C plus 1. And then this diagonal, R is C plus 2, and so on. What about this diagonal? In here, R is C minus 1 along this diagonal, and so on. So what happened is, if you actually look at any number, any particular point, and you look at R minus C, then everything along this diagonal has a value of 0. Everything along this diagonal has value of 1, minus 1, minus 2, minus 3, and so on, all the way to minus 7. Wait, I got the sign mixed up. Yeah, it's plus 3, 2, 1, and 0. And then on the other side, R minus C on this diagonal is minus 1, minus 2, all the way to minus 7. So what that means is, when I'm at a certain location, I look at the coordinates and compute this R minus C. That will give me a number that I can use to index, we call it diagonal 1. Okay, the corresponding diagonal numbered in this way. And then I can do it exactly the same as before and just say, okay, minus 2. So the diagonal for minus 2, it's now 1 more. And whenever one of these numbers has more than 1, you know that there are 2 queens on that diagonal. Now, you generally don't want to have an array with negative indices. So instead of R minus C, if you do R minus C plus 7, then this will map it from 0 to 14. And now you're okay. So you can have a diagonal bitmap, a Boolean array, or whatever you want to call it, that keeps track of how many, or whether you have a queen already on that diagonal, or you can count. Either way, you can use that to figure out quickly if you have two queens on the same diagonal in this way. So this is r minus c plus 7. What about the other type of diagonals, right? So if you look at the other type of diagonals, this one is just, okay, so here, so for, let's say this is 0, 2, 1, 1, 2, 0. If you add up r and c together, it's always 2. Let's look at this one. This is 0, 5, 1, 4, 2, 3, and so on. So if you add up r and c together, it's always 5. Why does it work? Because you start with 0, 5, and when you go this way, you increase row by 1, but you decrease column by 1. So when you look at r plus c, the net changes nothing. So with the diagonal D2, you do the same thing, except that you compute r plus c. And you would use the same kind of array from 0 to 14 to see if there are more than one queens in a particular diagonal in the other direction. So with that, you are able to figure out quickly if you have more than one queen in any of those 4 directions. And you don't have to actually scan everywhere. Okay, so let me just quickly show you. So I have arrays, 8 elements for the rows and columns to say how many queens there are on each row and column, and then that 2 diagonals, 15 of them from 0 to 14. And then this counts how many queens there are. I'm not quite sure why I have this variable line, but basically I just loop through, read the character. If it's a dot, nothing to do. Otherwise, there's a star, then that's a queen. Then I increment the corresponding diagonals and rows and column array. I guess I use r plus c for the first one and r minus c for this plus 7 for the second one instead of what I wrote here, but it's really the same thing. And then I add, count how many queens. Then here, the first thing I do is make sure that the number of queens is exactly 8, otherwise good is false. And then here, I just make sure that every row and every column has exactly one queen. I guess you can check that it's bigger than less than or equal to 1. But anyway, because I also checked that there are exactly 8 queens. But you know that in an 8 queens problem, you must have every row and every column have exactly one queen. However, not every diagonal will have a queen. So here I just make sure that every diagonal, it's at most one queen. Now, you might not be familiar with what I'm doing here. I'm taking a Boolean variable and I'm taking that Boolean variable and this condition. So if this was already false, if good was already false, it doesn't matter, it remains false. But if this was true, it will remain true as long as this condition I just checked is still true. So basically, it's a way for me to check that every single condition is satisfied. If any one of them is not, this will be false. And then, of course, at the end, I print out valid or invalid based on whether my flag is still true, whether it's still true. So here, I guess I'm also in some way that it's a little bit different. I'm still using tables to simplify, my logic, so I don't have to do the search on the whole line. But my table this time is not like an input table that I hard coded in, but rather a table that I use to store how many queens are on a certain line. Okay. Next one. Knight jump. So now this one basically tells you that you can jump, a knight can move in these certain ways as long as it's within bounds. and you want to start wherever you are and move to the upper left corner with the smallest number of moves, and -1 if not possible. So if you have taken 3620, then this is a fairly classic problem called breadth first search. And you just implement breadth first search. But if you have not taken that, I guess maybe you should read up on what breadth first search is before you come back to look at this. But what I want to talk to you about, if for those of you that know what breadth first search is and try to implement this, is how do you actually implement this movement of the knight, right? There are 8 different places it can go to. Basically, move one step in one direction and 2 steps in the other orthogonal direction, and there are 8 possibilities. And what you don't want to do is write it 8 times. So the classical way of dealing with this is to realize that if you start from RC, you can move to +2 and +1, +2 and -1, -2 and +1, and so on. And so it's better just to code this as a table of 8 displacements and then loop through them, which is what I'm doing here. So there's 2, 1. So dr and dc displacements in row and column. The first direction is 2 and 1, then 2 and -1, then -2 and 1, and so on. So I basically just look at this list and I coded it into this 2 arrays. Why do I do that? Because all I have to do now is just loop through this array 8 times, and I don't have to write similar but slightly different code 8 times based on these numbers. And then the rest of the stuff is just breadth first search. So for example, here I just have a distance array that remembers that everything is unreachable at the beginning, right? Nothing is reachable. Then I use a queue that remembers where I am right now, where I still have to explore. I push the initial position of the knight and into the queue and set the distance to 0. And while the queue is not empty, I pull out whatever is in the front of the queue, pop it. If I'm at the destination already, I'm done, I can return. Otherwise, here's what I'm doing here. I go through the 8 directions, the new coordinates R2 and C2 are just an old coordinate plus the displacement. And then I make sure that I didn't go out of bounds. And I make sure that I didn't get into an unpassable square. And then here I just check that if I've already been there before, then breadth first search says, if I've already been there before, I'm not going to find a shorter way now. So I'm just going to ignore it. And if I pass all these checks, then the distance of this place that I have just discovered, it's whatever the distance of the previous place is plus 1 more step. And then I push it into the queue and just keep going. So if you know breadth first search, then this should be fairly familiar. If you don't know breadth first search, then I guess you would need to go and look at some example breadth first search and learn what that is and then see how it's implemented. All right, now the last problem. The last problem is the one that is probably most challenging and what I would say hopefully educational for most of you. So there'll be something that you have never seen before for many of you. Okay, so here you have a sequence of numbers. Okay, so you have a sequence of numbers. How many are there? There are up to 1 million numbers. And in these sequence of numbers, you want to look for consecutive or contiguous sequence, subsequence of length m, which can be up to 10,000. And in there, you want to know if the maximum, so where is it? If the lowest and highest value does not, the difference between the lowest and highest value does not exceed a certain threshold. So basically, I have this long sequence of numbers. I want to know which of out of this long sequence, which interval of m numbers will satisfy that the difference between the max and the min is less than or equal to C. Okay, so let's start from here. I have a very big list of numbers, and I am looking at possibly m of them. And inside here, I want to know what is the max, what is the min, and I want to know if the max and the min, the difference, it's less than or equal to C. And if it is, I want to print out the start of this window, the index, where this window starts, and I want to print out all possible windows. Okay, so let's think about the most naive way of doing this. Right, so what is the most naive way of doing it? I basically look at all possible starting points. For each starting point, I'm going to scan forward m steps, finding the minimum and maximum, right? Subtract them, figure out if the difference is less than or equal to C, and if so, print out the value, right? So basically, I scan every single possible starting point. So there are n starting points. Then for each starting point, I scan the whole window while I keep track of the minimum and maximum, and then at the end I can subtract max minus min and see where that goes. The problem is, okay, what's the problem? The problem is n, it's up to 1 million, and m is up to 10,000. So if you just do it this way, n times m is up to 10 billion, which is way too slow. Okay, so let's just very quickly look and see how much time we're supposed to. 2 seconds. So it's not 1 second, so it's more than 1 second, it's 2, but no way you can do 10 billion things. Okay, so that's not possible. All right, so back to the drawing board, as we say. What are we going to do? Now, the standard thing that we have here, well, I should say, I guess if you've seen enough of this type of problems, it's standard. These are sometimes called a sliding window problem. Right? You have this window of m things, and you need to process all possible windows. All right? And the way, why is it called sliding? The idea is that when you process one window, maybe you can process the next window in a better way. So for example, the next window, let me use a different color. It's like this. So a new element enter into the window, but you have an element that leaves. Okay? So the question is it possible that instead of rescanning the entire window when we move the window by one, is it possible to just somehow, not figure out the max and min all over again, but get rid of the thing that was leaving, insert the thing that is now here, new, and do a little bit of adjustments and then figure out what the min and max is without scanning the whole window all over again. That is the idea. Now, what you want to do, I guess, is have a data structure that allows you to do what? Allows you to keep track of minimum. Let's just say minimum for now. If you know how to keep track of minimum, you can figure out how to keep track of maximum. of a bunch of numbers, it allows you to add an element and allows you to remove an element. And of course, when you add and subtract, remove elements, uh, your minimum, it's going to be updated. So it's always going to give you the minimum of what's in there. And then you say, okay, well, okay, what are some of the standard dated structures that we know? And you might think, oh, wait, there's something called priority queue, which allows you to keep, let's say, the maximum or minimum. But priority queue doesn't work. Why? Priority queue, of course, can keep track of minimum. That's no problem. You can add elements. The problem is you cannot remove a specific element. You can only remove the min. If what you're shifting out of the window is not the min, priority queue will not help you. And there's no easy way to stick your hand into a priority queue to look for a particular thing to get rid of. Okay, you can only remove the min. So priority queue is no good. What else can we do? Okay, what else can we do? What other data structures do we have that sort of keep things sorted? Well, another thing that you can use could be a binary tree, which in STL can come in the form of a set or multi-set. So let's say you have a binary tree, binary search tree. So in our case, in C++, there'll be a multi-set. So why multi? Because in this problem, it's also possible that you have a certain number appearing more than once. So if you just use a normal set, that will not work. You need to worry about a number occurring multiple times. So when you have a binary search tree, what's going to happen is you can keep the min and the max. How? Because here, when things are sorted, the begin of the container will point to the first element in the map and on the multi-set. So that's guaranteed to be a smallest one. And here, if you look at R begin, so I don't say and because and, remember, if you're familiar with C++ containers, and always it's one position too far. But R begin is the first element coming backwards. So R begin is actually the max. And now what do you do, right? Well, can you keep the min and max? Yes. You just look that up. But so this is looking that up, begin and end, maybe constant time, but or maybe if you have a binary tree, maybe log n time. But basically everything in binary tree is log n time at most. Adding an element, of course, it's log n time, and removing in a binary search tree or multi-set, you can indeed remove one single copy of an element. So you have to be a little bit careful. Okay. If you look at multi-set, okay, so if you were to erase, okay, so if you were to erase an element, it will erase all the copies. So you have to be a little bit careful how you erase. Okay, I don't know why it's taking a while. Let me I'm not quite sure something it's okay, but anyway, erase, it's a little bit trickier, so you have to be careful how you erase. Try a different site. Multi-set. So erase. So here, erase, if you erase with the value, all elements of that value is removed. Okay, so you don't necessarily want to do that, but what you do is you first find that element with, that will give you an iterator, which then allows you to erase one single copy. Okay, so you have to be a little bit careful there, but in any case, you can do it. So basically, all of these you can add element, you can remove elements, all of that can be log n time. Well, actually, in this case, it's log m time because the size of the windows is m. And so now you have n times log m, which should be fast enough because m is 10,000, log of m is pretty small. Okay, but that's not the best solution. We can, in fact, make it so that it's linear time with no log factor at all. And this is what I want to show you. It's a data structure that you probably have never heard of before. And here, the only reason why what I'm about to say works, it's because when you remove the element, it is always the first one in. So first one in this window. Or you can say the oldest one in the window. Okay, when you remove something, it is always the oldest one that you add to the window. And what that means is that you're looking at a queue where the minimum needs to be maintained. Okay, and again, I'm only talking about minimum, but if you know how to maintain the minimum, you can maintain the maximum too, but the same idea. Okay, so let's see. How do we maintain this? How do we have a queue that allows me to maintain the minimum? Let's call that a min queue. Okay, so let's think about some numbers. 2, 1, 5, 3, 4, 7, and I'm adding these things as I go. Okay, so what I'm going to do, believe it or not, is I'm going to use 2 stacks. I'm going to have stack 1 and stack 2. If I push into the queue, it always goes into stack 2. But when I pop, it always comes out of stack 1. Okay, it's a little bit weird. Why would I use a stack? So I'm going to push 2, 1, 5, and 3. So I'm going to push 2, I'm going to push 1, push 3, 5, push 3. Right? Okay, so not only am I not keeping track of the min, I'm actually completely in the wrong order. Because when I pull things out, it pulls 3 out first. So that's maybe not so great, I guess you can say. Okay, now what am I going to do? Okay, so now let's say I want to pop. Okay, so I've inserted these. If I want to pop, I'm only going to pop from stack 1, but there's nothing in stack 1. So what do I do? Anytime I want to pop, if there's nothing there, I will pop the stack 2 and push it into stack 1. So it reverses everything. And now stack 2 is empty. Okay, and now if you want to pop, you'll first pull out the 2, then you'll pull out the 1, you'll pull out the 5, you'll pull out 3, and now it's going to be in the correct order. Okay, so all of that seems a little bit complicated. Why do we do this? Okay, so let's move it back to where we were before. What I'm going to do is I'm also going to remember, actually I don't need this. I'm going to remember the minimum of everything that I have in stack 2. So right now, as I push things, I can update the minimum. But if I empty it by moving everything to the other side, then it'll become infinity. Because as it's empty stack, the minimum is infinity. Okay, now, what happens when I put this 3 over? Right now, minimum is infinity because it's empty. This stack is not going to just store 3. It's actually going to store a pair. It's going to store the elements 3 and the previous minimum. So the previous minimum was infinity. When I put the 3 over, this becomes 3. Okay, then this comes over. It puts on here, and the minimum is still 3. The previous minimum is 3. 5, it's not bigger, it's not smaller than 3, so the minimum is still 3. Now I put this over, become 1 and 3 because that's the previous minimum. And now the minimum is 1. And then finally I put this over to here. It'll look like this. And this will now be empty. And this will be infinity again. So what is the minimum of this whole queue right now? The minimum is the minimum of these two numbers, which in this case is 1. So now I put 2. So I pop. So I pop the 2. Great. But as I pop, remember why I have this number. This is the previous minimum, which is 1. So I basically take this number and overwrite this one, which in this case nothing happens because it doesn't change. And then I pull 1 out. And now when I pull 1 out, 1 is no longer the minimum, but what is the minimum? I can use that to restore this 3. So basically the second element in my pairs, it's going to be used to allow to restore this minimum to the previous step when I put them up. And later on, let's say maybe I push a 4, so I push a 4 here. So this minimum becomes a 4. And then I don't know, maybe there's a 0 here. So I push a 0, and this minimum becomes a 0. And if I were to ask what is the smallest element in the window, it's the minimum of 3 and 0, which is 0. And basically that's how this minimum stack, the minimum queue works, by using 2 stacks. Now, there are 2 stacks. Things are moving from one place to another. What's the complexity? If it's just 1 stack or 1 queue, then basically everything is constant time. When I push, it's constant time. I just push. Yeah? I just touch stack 2. That's easy. When I pop, if there's something already here in stack 1, then I just take out this previous entry. No problem. The top entry. But if this was empty, I'm going to have to take all of these things and transfer it over here. So a particular pop may involve many operations because it might have to empty the stack too. However, if you think about another way, every element will enter stack 2 once. It will be pulled into stack 1 once, and it will be eventually pulled out at most once. So if you look at every element, it can really have at most 3 different things that can be done to it. Push into stack 2, move over to stack 1, and pop out of stack 1. So if you have 1,000 things that you might be pushing into this queue and popping, each of those 1,000 things can only do at most 3 things. So therefore, over the lifetime of the algorithm, every element can move within the queues and then have at most 3 different things done to it. So on average, overall, the total number of operations that you do is basically 3 times n, where n is the number of things that has ever entered or left the queue. Even though some pop operations may require many steps, overall, this big penalty of moving things from stack 2 to stack 1 can only occur once per element. So basically, that's it. You use this min-q data structure. Once you figure out how to program this, then you can implement the sliding window algorithm to do this. Now, what about max-q? Well, you can keep the max too, or if you already have a data structure called min-q, you could just use that again, but this time push the negative numbers out into the queue. So negative numbers, the minimum negative numbers are basically a maximum of the positive numbers. Because when you multiply things by -1, everything, it's basically switches direction from min to max and vice versa. Now, what did it call? Sound. Okay, so first of all, I have this min-q. There's this S1, which is a stack of pairs, stack 2, which is S2, just an integers, and then there's M1 and M2, which are the minimum of each of these stacks. And then there's push and pop, which implement what I said. We'll go back to this later. Okay, so how do I implement this, right? So I have two queues, one for min and one for max. As I said, you can change this min queue to keep track of both min and max, but because I already have this code, I just didn't bother changing that, and I just used two queues. So here I read in all the input, and then there's one single thing that there's one special case you have to worry about. Maybe you cannot have any windows to begin with because nothing in the problem statement says that the size of window M is not bigger than the number of elements in the list. So if you want windows of size 1000, but the number of elements in this sequence originally only is 10, then that doesn't work. Okay, now assuming that there's at least one window, what do? I first deal with the first window. Okay, so the first M values, and then check if the max. So because I use the negative min q to keep the max, this looks a little bit funny. I pull out the min from the max q and negate it, and then subtract the min. If it's less than or equal to C, then I print out something, and I remember that I found something. Then here, this is where I do my sliding window. I basically loop through all the windows. I push in the new one. I get rid of the old one as I slide. I have to do it twice because one for the min queue and one for the max queue. And then I just ask if the max and the min have difference less than or equal to C. And that's it. And then at the end, if I have not found anything, I have to print none. Now, I want to show you in my code library, and this is something that you have access to, everybody have access to, and it's allowed in a programming competition. I have something called a source directory. You can look at index to see what's in there. This min queue is not there. Okay. Now, there's a separate directory called ICPC, which is what we took when we went on to higher level of competitions like North American Championship or World Finals with much stricter page limits and such. And we have different versions. I guess the most recent version is 2020 North American Championship where we went to, and min-q is here. So this is where I pulled it up. Now, maybe you don't want to use this code, maybe you want to do it yourself. With the explanation I give you before, hopefully you can write this yourself, but you can always look at this, right? So I have two queues, and then when I push, I just push into this, two stacks. I just push into the second stack, update the minimum. But when I in front, I always pop the first one from stack 1. But before that, I have to move potentially. And move basically, if the stack 1 is not empty, there's nothing to do. However, if it is empty, then I got to empty stack 2 and just keep popping the top thing from S2 and basically move it to S1, and then with remembering um, the previous minimum as we go. Ins max is the infinity that I talked about. So basically, you've initialized M2 and M1 appropriately as you go. So that's basically I want to introduce to you two different things, I guess. First thing is the sliding window idea, and that's a very common technique when you want to process windows in a big array. Try to figure out how you can incrementally keep track of stuff uh, and then update things as you add one more things and remove one thing that leaves the window instead of recomputing everything. Okay, and then the second thing is to introduce some kind of data structures that keep track of minimum and maximum as you go. A multi-set will work, but the data structures that I just described will be quite a bit faster. Okay, so that's it for this week. As usual, if you have any questions, you can ask me. Otherwise, I'll talk to you again the following week.